So what if our cosmic search for neighbors has been a bit, well, nearsighted?
Nearsighted how?
Like, have we been so focused, maybe too focused, on finding Earth-like planets?
Ah, I see where you're going in.
Yeah, have we completely overlooked a whole other category?
Yeah.
Worlds orbiting, the giant planets. I mean, moons.
Exactly. Yeah, today we're really diving into exomoons, moons orbiting planets outside our solar system,
Okay.
and exploring the very real possibility that these could be prime locations for life.
Right.
We're digging into this really interesting study. It's by Zoltan Deniks and his colleagues. They use some, frankly, incredibly complex simulations to try and figure out how these exomoons might actually form around really massive planets.
Okay, so the mission for you listening then is to really get a handle on how these potentially habitable exomoons could, pop into existence around these huge gas and ice giants.
And it's not just a wild idea, is it?
No, not at all. We're talking, around 6,000 giant exoplanets already found?
Roughly, yeah. Within the habitable zones of their stars.
Right, the zone where water could be liquid. And each one of those giants could potentially host multiple moons.
The scale is just huge.
It's mind-boggling. Okay, let's get down to the nitty-gritty then. The first big hurdle, I guess, is just how these moons even form in the first place.
That's the core question. So the
Right.
researchers, they essentially built these virtual planetary systems, but centered on a giant planet, not a star.
Okay.
Imagine that swirling disk of gas and dust, like the one that formed our solar system, right?
Yeah.
But smaller, circling a giant planet. That's your circumplanetary disk.
Got it.
They then populated these virtual disks with lots of lunar embryos, sort of like baby moons, and even smaller bits, satellitesmals, and they tracked
Everything, like collisions, mergers.
collisions, mergers, yeah, even things getting kicked out of the system entirely. The big question was, how much of that starting material, that disk stuff, can actually clump together and form, proper moons?
But it's not going to be neat and tidy, I imagine. There must be a lot of chaos, stuff getting lost.
Precisely. Yeah, these circumplanetary disks, they're not static. They tend to lose material over time. And what's really interesting is the difference the simulations found between what they called cold disks.
Cold disks, meaning?
Relatively close to the star, say within about 1 AU, like Earth's distance from our sun.
Okay.
And contrast those with hot disks, or maybe more accurately, models focused just on the planet's immediate environment.
And the difference was?
Mass loss. Those colder disks, closer to the star, they tended to lose a fair bit of mass, maybe 30 to 40%.
Why?
Well, as these baby moons form and stir things up, they can fling debris outwards. But the hotter environments, closer around the giant planets, much better at hanging onto their material. They retained over 90% of the initial mass in the simulations.
Wow, over 90%.
Yeah. So the key takeaway there is that these hotter planet-centric environments seem much better suited for building really substantial moons. The kind that might actually hold on to an atmosphere or keep warm inside.
Okay, so if we want big, potentially habitable moons, then maybe we should be looking at planets further out where these hotter disk conditions might happen. Seems logical, right? More material means bigger moons.
Well, not quite so simple, and this is where it gets really, really interesting.
Oh.
The researchers found that moon formation efficiency isn't uniform, it peaks. There's a kind of sweet spot.
A sweet spot. Where?
Around 2 AU from the star, so twice Earth's distance from the sun, roughly.
2 AU. Why there?
Yeah.
What's so special about that neighborhood for making moons?
It seems to be this delicate balance, closer in, like within that 1 AU range with the cold disks.
Yeah.
The star's intense radiation plus all the disk activity, it just strips away too much material. It hinders the growth of big moons.
Okay, too disruptive.
Right. But then if you go much further out, well, you might get really massive disks to start with.
More material, like I thought.
Yeah, but they tend to churn out a lot of smaller moons, maybe none massive enough to be truly habitable long term. They might lack atmospheres or internal heat.
So less focused formation.
Kind of. That 2 AU mark seems to be this Goldilocks zone. The planet's gravity is strong enough to gather a good amount of material, build efficiently, but it's far enough out that the star isn't constantly sandblasting the disk and messing things up too badly.
Yes.
It's a balance between the star's influence and the planet's.
That's really counterintuitive. I definitely would have bet on bigger disks further out making bigger moons.
Okay, so we've got a potential mechanism and a sweet spot for forming these moons. But then, the big question, could they actually support life? Be habitable?
Right, the habitability question. And the key ingredient, as far as we know it, is liquid water.
Always comes back to water.
Pretty much. And for that, you need energy. Heat. Exomoons have two main potential sources. First, stellar irradiation, just the heat and light from their star, like Earth gets from the sun.
Makes sense.
And the second?
Tidal heating.
Ah, yes. Like Jupiter's moon Europa or Saturn's Enceladus.
Yeah.
The planet's gravity constantly squeezing and stretching the moon.
Exactly. That gravitational tug-of-war flexes the moon's interior, generating heat through friction.
Even if the surface is icy.
Absolutely. It could maintain huge subsurface oceans. And here's the thing. Beyond about 1 AU from the star, that tidal heating often becomes the dominant energy source for an exomoon.
More important than a star's light.
Potentially, yes, especially for keeping deep water liquid. But now think about that 1 to 2 AU sweet spot again.
Formation sweet spot.
Yes, it pops up again, but now for habitability, because within that range, you have a better chance of getting both significant stellar heating and significant tidal heating working together.
A double whammy of energy.
Precisely. And that combination, that's what could potentially allow liquid water, maybe even on the surface of an Earth-mass moon, orbiting a giant planet in that zone. It really forces us to rethink what habitable even means.
So let me get this straight. These giant planets, which we usually think of as just huge, cold, maybe stormy gas balls.
Pretty much, yeah.
They could actually be orbited by moons that are potentially much more hospitable. Moons with liquid water, maybe even surface water.
That's what the physics suggests is possible.
Wow. That just dramatically expands the search area, doesn't it? The potential real estate for life.
It really does. The researchers' key findings really hammer this home, their analysis, looking at hundreds of known giant exoplanets.
Yeah.
It suggests that moons from Mars-sized up to Earth-size can realistically form around giant planets, provided the planet is massive enough, say, at least 10 times Jupiter's mass.
Okay, so super Jupiters.
Generally, yes.
Right.
And the highest potential for habitability, again, consistently shows up in that 1 to 2 AU range from sun-like stars. The strong implication is we might have just been overlooking a huge number of potential habitats because we were just focused on the planets themselves.
It really makes you wonder, doesn't it? Like we've been searching for Earth 2.0 and missed a whole archipelago of potentially habitable islands orbiting these gas giants.
A great analogy.
So if these things are theoretically plausible, maybe even common, why haven't we found a bunch already? What's the holdup?
Well, that's the next massive challenge, isn't it? Detection.
Hard to see them.
Incredibly hard. Think about it. You're looking for a relatively tiny object orbiting a huge, bright planet, which itself is orbiting a distant star. The moon's signal's just drowned out. It's faint. It's close to the planet. Our current tools really struggle with that directly.
Okay, so it's a tech limitation.
Largely, yes. But the tech landscape is starting to change.
The cavalry's arriving. What we got coming?
Well, we're already seeing some really exciting, though still tentative, results coming from the James Webb Space Telescope, JWST.
Right, Webb's amazing.
Its sensitivity, especially in infrared light, is giving us our best look yet. People are actively analyzing data for potential exomoon candidates right now. We're waiting for those confirmations.
Fingers crossed. And beyond Webb.
Looking a bit further out, there's the European Space Agency's Plato mission. Yeah, launching later this decade. It's designed specifically to find exoplanets by watching them transit or pass in front of their stars.
Okay.
And its method, looking for those tiny dips in starlight, also gives it a much better chance of indirectly spotting exomoons. By looking for slight variations in the timing or duration of the planet's transit caused by the moon's gravity.
So the moon tugging on the planet changes the timing just enough to be detectable.
That's the idea. It's subtle, but Plato should be sensitive enough to pick up quite a few candidates, if they're there in the systems it observes.
So the first confirmed habitable exomoon. It might not be science fiction for much longer.
It could absolutely be a reality within, say, the next decade or so. It's genuinely exciting.
Unbelievably exciting. Okay, so let's bring this all together then. This deep dive really highlights that our search for life needs to broaden its horizons, doesn't it?
Absolutely. We shouldn't just be looking at Earth clones. The habitable zone around a star effectively gets wider, you could say, because it now includes these potential moons orbiting giant planets.
Especially those giants sitting in that 1 to 2 AU range.
Exactly. That seems to be the prime territory according to these simulations.
So if astronomers can focus their observations, maybe prioritize giant planets in that zone around sun-like stars.
They significantly boost their chances of finding these potentially habitable exomoons. It gives us a search strategy.
Right. And it just makes you think, doesn't it, about the sheer variety of places life might pop up.
It really is.
Maybe the next huge discovery, the proof of life beyond Earth, it might not be on a planet at all.
It could very well be on a moon tied to a giant world, maybe with strange tides and a different kind of sky, fundamentally shifting our whole perspective on where life belongs in the universe.